In continuation with the concepts of small signal amplifier, we'll solve some few problems based on biasing of the bipolar junction transistor. The contents are numericals on self bias small signal amplifier. Here I am solving 3 problems for you all. Then numericals on voltage divider small signal amplifier. 2 problems I will discuss, and the last problem is an exercise for students community, and any problem if they are there we'll discuss in the live session in the coming 12th lecture. Okay, this is an emitter bias circuit. Fine. Here there should be a connection of 12 volts, and here this is an input impedance that you are supposed to find. Output impedance Z0, RC is 2.2 kilo ohms, RB is 220 kilo ohms, and R0 is 40 kilo ohms, beta is equal to 60 kilo ohms. Problem description. In this problem you are supposed to do the AC analysis to find out the input impedance Z, input impedance Zi, output impedance Z0, and find the overall find out the voltage gain in the active device, not the overall voltage gain. Repeat the part A and B of the main problem when R0 has changed to 20 kilo ohms. So from here your AC analysis starts. So draw the AC equivalent circuit now first. So RE, then beta IB, then comes your resistance R0, then comes your resistance RC, this is your emitter, ground is, this is your collector, then between the base and the ground there is resistance RB, so from here you will find out input impedance Zi, AC equivalent circuit, using RE model. So RB, the input resistance, is nothing but RB parallel beta times RE. Now why that beta is coming over here? Go through your analysis. What we have done for our emitter bias common emitter configuration amplifier. So the current flowing actually into the base terminal is nothing but your IC. So it is taken as beta times RE. This RE you have already found out in previous slide. So it comes out to be 496 ohms input impedance. After substituting the various values of RB and taking and solving it, you get this a value of input impedance. Next, output impedance. Since R0 is greater than 10 times RC, just take the output part. Since I am interested only in the output part, here current source will be open circuit in parallel with R0, and this is RC. Find out your input output impedance by looking back into the network. So Z0, here it is mentioned that R0 is greater than 10 times RC. So Z0 will be directly equal to RC. This has simplified your relation. So Z0 is equal to 2.2K. Now coming to the voltage gain AV. What is the voltage drop? Take the parallel combination of RC parallel I0. Current flowing out of it is IC. So IC into RC parallel R0. What is the input side? It is nothing but an emitter resistance RE. So current flowing into it is IV. So your output voltage V0 is equal to IC in bracket RC parallel R0, then VI, this is equal to IB times RE. So knowing the value of V0 and VI, you take the ratio of the output voltage upon input voltage. That will give you a voltage gain. V0 is equal to AV, voltage gain AV is equal to V0 upon VI. For this IC, you substitute beta times IB. So beta into parallel combination of RC parallel R0 upon the input voltage, that is RE. So in this way this relation has come. This particular relation. And you get the value of voltage gain AV as minus 265 when you are substituting various values. Okay. So you can see we have found out by considering two particular relations. When R0 is defined in this relation, and in this relation R0 is not defined. So what happens is that the gain will increase when we are not considering R0, but when we are considering R0, that time gain will reduce. Now in the similar way, when R0 is brought down from 50k, 40k to 20k, try to find out the values. So you go through the presentation thoroughly in this video that is given and try to solve in the similar way. So input impedance, you can see that input impedance, it is not changed. R0 output impedance also remains the same, fine. But what will happen is that the gain will change. Now here when R0 is reduced, obviously when R0 was 40k, that time gain observed was very low. But when the resistance R0 is brought down, the gain will increase. So draw the AC equivalent. Step 1, short circuit the capacitors and short the DC sources. We have already done. So what we are trying to do is we are trying to find the impedance Zi from the input side. So you can see that it's a parallel combination of 390 kilo ohms parallel RE. So RE value that comes out, Zi comes out to be 1.3 ohms. Next impedance Z0, it is RC parallel R0. AV is minus RC minus IC into RC parallel R0 upon IB times RE. So substitute the value of IC, which is equal to beta times IB. So you will find that some parameter, base current parameter cancels out from numerator and denominator, giving you a simplified relation of the voltage gain, that is minus beta into RC parallel R0 upon RE parallel 390. So substitute all these values and you should get the relation. Now this particular condition comes when this is the overall voltage gain. So that is why this factor 390 kilo ohms have come into picture. Here we are simply considering across RE. So I'll just draw the input condition. This is your RE. Fine. RB. So this is AV. And this is your overall voltage gain. Fine. So input side, AC equivalent circuit. Right. So they should understand the problem, I guess. Next, take the third problem for your common emitter self-bias circuit. Here the resistance combination RB is connected to collector. Previously through base it was given to some supply, that is VBB. Now here it is connected to VCC. So for the network, the gain is given and you are supposed to find the voltage VCC. A reverse way of problem. From AC analysis you are entering into DC analysis. So voltage gain for this particular circuit is given by minus RC upon RE. So directly substitute the value, you will get the value of RE as 29 ohms. In present case, again your emitter current is equal to collector current, as emitter is grounded. RE we already calculated 26 milliampere volts upon IC. So from this you utilize the factor, knowing the value of RE, you can find out IC. So IC is equal to 26 millivolts upon 29. So it comes out to be 0.89 milliamperes. Find out the base voltage VB. VB is almost proportional to VBE, as VE is equal to 0. The base voltage is equal to the forward biasing voltage 0.7 volts generally taken for silicon transistor. Then the base current IB is equal to IB IC upon beta, which is equal to 9.8 microamperes. So after substituting the values, it gives you answer as 9.8 microamperes. So apply KVL in the input loop. The another way, because we are in a position to find out the voltage VCC, so knowing the values of the base voltage VB, IB and RB, we will be in a status to find out the actual DC voltage VCC, which is may be shown in the previous incoming slides. So here it is solved for you. So VCC is 9.1 volt. So this completes your AC and DC analysis for self-bias common emitter amplifier of BJT. Next we will see a voltage divider network, a BJT small signal amplifier. So common emitter configuration. First try to understand what is a common emitter configuration. So this is your overall common emitter configuration. R1, R2, RC, RE. These are the coupled capacitor, CE. These are your bypass capacitors, input and output bypass capacitor. The role of this bypass capacitor is to separate the DC signal from the AC signal. Now what is this capacitor doing? CC. It is separating your output signal from the voltage VCC. Similarly, if at all this bypass capacitor is there, it is separating the input signal VI from the DC voltage source VCC. And here the coupling capacitor, bypass capacitor is connected, coupling capacitor, CE. CE is your coupling capacitor. So what it will do is, it will act as an short circuit at a higher frequency, at higher operation frequency around say 1 kilohertz onwards. So this resistance RE will be short circuited. So due to that, what will happen is that there will be improvement in the voltage gain. So utilization of this part of the circuit is to improve the voltage gain at higher frequency. So for the network shown, determine the value of RE, calculate ZI, ZV, find AV. Repeat part B and C for R0 is equal to 25 kilo ohms. Why it is saying B and C? Effectively it is observed that the output impedance and the voltage gain are going to change. RE is given to you, right? Rather you will have to find out. So for the network shown, determine the value of VCC, that is AV is equal to minus 160 and R0 is equal to 100 ohms. The network is same as the previous problem. So what you do is you check the solution, check whether it is sustainable for stability. So beta RE should be greater than 10 times R2. So here it is satisfying the relation 100 kilo ohms is greater than 56 kilo ohms. So satisfying this situation and suggesting you that circuit is stable and can be operated as a common emitter amplifier. So take R0 is greater than or equal to 10 times RC. Then you will be able to find out the voltage gain AV since it is stable, and here what it has happened is that AV is known, so you are substituting that value and calculating RE. So RE is coming out this much over here. Use this for finding out the current IE, so which comes out to be 1.261 milliamperes. This should be in continuation with the first problem of the voltage divider network. Slide transparency changes. So Zi is equal to R1 parallel R2 parallel beta times Re. So this will give you this much value. R0 is greater than 10 times Rc. So Z0 is directly equal to 3.9 kilo ohms. So AV is equal to minus Rc upon Re, that is equal to minus 127.6. Now previously here R0 was 50k. Now we have reduced it down to 25k. So Zi remains unchanged. Z0 is equal to 3.9 kilo ohms parallel 25 kilo ohms. Substitute this and calculate the value. What will be the voltage gain changed? So voltage gain has come down to minus 110.28 when it was when R0 was 40k, that time it was 127.6. So you can see that when R0 is reduced, the voltage gain also reduces. Okay, that is what we are comparing. So let us draw an AC equivalent circuit so that it will make you more understandable. AC equivalent circuit. Fine. So here we had input resistance R2 and R1. Fine. So RE model, with the help of RE model I am drawing. So this is your RE, right? Here it's a combination of R1, R2. This is R1. R2. Okay. Now we had a capacitor over here, so that is shorted. Fine. So this is your input side. So base to emitter. Fine. Now this is your base terminal. Suppose complete throughout. Now at base terminal you might be remembering there was a resistance Re along with the coupled capacitor Ce. So at higher frequency that capacitor gets shorted. So when a shorting effect is shown across any terminal, across any component, it is as good as shorted. So that is why your emitter resistance is shorted. So Re I am writing here. Practically you have to picturize and understand that it is a shorting effect, as Re is equal to 0 ohms fine. Then between the collector and the emitter terminal there is a current source which is beta IB. Then along with this there is R0 Then between the collector and the emitter terminal, which is at ground, there is a resistance RC. So instead of drawing in this terminal, I'll draw over here only. So it will be quite clear when you are solving your problem. So this is your RC. Fine. So here you are measuring your V0. Here you are measuring, giving an input signal Vi. So this is equal to R dash according to the book convention. So you are going to find out the input impedance by looking into the terminal of the input terminal of the network. So Zi. So Zi is a parallel combination of R1, R2, R2 parallel R1 parallel Re, which is given over here. Fine. Now coming to this side, this is your Z0 output impedance looking back into the network. Z0. So when you are finding out Z0, you have to open the input, you have to open the current terminal. So that will act as an open circuit. Z0 is equal to parallel combination of R0 parallel RC. So it's a product of R0 RC upon R0 plus RC. Now we have defined a relation over here that R0 is very much greater than RC. Therefore, your Z0 comes out to be RC. Now coming to a voltage gain, AV. Actually, we are considering the input across the base to emitter. So this is your actual Vi, what we consider. We are not calculating the overall voltage gain. We are calculating the voltage gain only for this combination. AV. So that is why AV is equal to minus why? Because the current is flowing out of the terminal. So here minus beta times IB, since it is IC is substituted by beta times IB. So beta times IB into parallel combination of R0 RC. Already we have seen in the output impedance that since R0 is greater than 10 times RC, so your output impedance is going to be RC itself. Upon the input current flowing into the base, this is IB. So this will be IB times RE. So you cancel out the common term in parameter, that is IB. So it comes out to be beta times RC upon RE. Fine. That's how your problem is changed over here. Fine. This particular slide or this particular presentation refers to a problem number 1 of voltage divider network, voltage divider biasing network of common emitter amplifier using BJT. And this particular problem refers to problem 2 of voltage divider combination, voltage divider bias. Bias CE amplifier. Okay. So in second problem, what was given was that the voltage gain was given and you were supposed to find out the value of Vc. Fine. So we have come to a situation where we have found out small Re and we were in a position to find out the voltage emitter voltage, and accordingly find out Vb and relate Vb with Vcc. That completes the problem. Second problem over here. A slight activity for the students. So for the given network, here just analyze the configuration very thoroughly. I'm just giving you the clue and a hint to solve this problem. So do a DC analysis that will help you in finding Re. Then you find out the values of the base terminal and the collector terminal. Later on, you redraw the AC equivalent circuit, Zi and AV. Then find out the input impedance and the voltage gain. Okay, try yourself. If you don't know, we will solve it in the live session at the 12th lecture from the begin of the session.